Hi, I'm Alistair, and I make games and playful experiences using technology. And in this video, I'd like to teach you how to make an escape room puzzle that uses a magnetic sensor input. Now, that might mean a reed switch like this one, or a hall sensor such as this one. And these are both very common types of input used in escape room puzzles. So if you've ever played a game in which you need to position a dragon's egg back in a nest, or perhaps take a chess piece and move it to a particular square on a chessboard, or maybe you have some books that need to be rearranged on a shelf, there's a very good chance that that puzzle had a magnet embedded in the prop that was detected by a sensor such as these. Now, from a technology point of view, puzzles such as this are actually very easy to create. Sensors such as these are cheap and readily available, and if you look on the internet you'll be able to find code samples that show how to use them with an Arduino or a Raspberry Pi to create a prop controller. But one thing I haven't really seen anywhere is somewhere that compares the properties of different sorts of sensors. When should you use a reed switch or a hall sensor? And particularly in the context of an escape room puzzle, what's the most appropriate hardware to use? So that's what I plan to talk about in this video. So before we take a look at the magnetic sensors, let's take a closer look at the magnets themselves. And the sort of magnets you're going to want to use for a prop like this are typically permanent rare earth magnets or neodymium magnets. And they come in a range of shapes and styles and sizes, so I've got a handful of different ones here. Now, these will typically be mounted in the portable component of your puzzle. So they are in the chess piece, or in the library book, or in the dragon's egg. Whereas the magnetic sensor will be in the permanent part that is non-movable. So that would be the chessboard or the bookshelf. The reason for this is obviously that permanent magnets do not require any power source. They do not wear out. They don't require any maintenance. So you can secure these inside the body of your portable prop and they will just stay there continuing to function as you need them to. I tend to prefer this style of magnet, so I've got a disc here or an oblong here that have pre-drilled holes in them. Rare earth magnets can be very brittle, and the stronger the magnet, the more brittle they typically are. So when you're trying to secure them, it can be easy to crack them accidentally and break them. But if you get these ones that have been pre-drilled, you'll find it relatively easy to secure them into your puzzle component just using a single screw. Now, the strength of a neodymium magnet is expressed using a grading system which has a letter and a number. So here I've got some N35 magnets, and you'll also find N42, N52 magnets and various other values. And this represents the maximum pull force of the magnet. Higher numbers means a stronger magnet. And if you double the N number, you'll get approximately double the pull force. So if you're looking for the highest strength magnet possible in the smallest possible package, grade N52 is the strongest commonly available. However, that's also the most expensive and is also the most brittle and hardest to work with. It's also worth remembering that larger magnets are stronger than smaller magnets. So if you choose to use a larger N42 magnet, you'll end up with the same pull force as you would from using a smaller N52 magnet, for example. So what strength magnet do you need to choose? Well, what you want is a magnet that's strong enough that it will definitely be detected by the sensor when the prop is set to the correct position, but not so strong that you're getting false positive readings when it's not quite lined up correctly. And the exact value is going to depend on a combination both of the magnet itself and also of the positioning and type of sensor you're using. So now let's take a look at the different sorts of sensors available. So there are two basic magnetic sensors that can be used in a puzzle such as this. There are reed switches and hall sensors. And in many ER puzzles, you could use either interchangeably, although they work in very different ways. And there are some situations where you definitely favour one over another. So this is a reed switch, and it consists of two metal reeds inside a glass capsule. And the reeds themselves are bent slightly apart from each other, so they don't normally conduct electricity. There's a small gap between them. As a magnet is brought closer to them, however, the metal is attracted to the magnet. It causes the reeds to snap closed, forming a complete circuit. So in its default state, this is like an open switch. No current can be conducted across the reed switch as there's a gap in it. As a magnet is brought closer, there comes a certain point where the magnetic attraction forces those two reeds to snap shut, and when they do so, the switch is closed and current can flow across it. So it's like a binary switch. It's either open or closed, and there's no states in between at all. Now, this is a Hall sensor, and notice how compared to the reed switch, which simply had two legs, a Hall sensor has three legs. And the reason for this is that rather than being a simple mechanical switch, this is an electronic switch and therefore actually requires to be powered. Now, this particular Hall sensor requires a 5-volt positive supply on one of the legs. It needs to be grounded on one of the legs, and then the third leg here gives an output that is proportional to the magnetic field that is detected. But actually, whereas reed switches are relatively straightforward and work in the same way every time, Hall sensors come in lots of different varieties. So let's take a closer look at some of the more details about them. So this is the first sensor I'm going to look at. It's the SS49E, and you can buy 10 of them on eBay for under £1. So these are under 10p each for the sensor. And if I load up the datasheet here and have a look through, let's see whether these are suitable or not. So picking out some of the relevant points here, it says that the linear sourcing output voltage, so this is the voltage you get on the output pin, is set by the supply voltage and varies in proportion to the strength of the magnetic field. So this is exactly what we would normally want and look for in a sensor like this. We have an output voltage that varies depending on the magnetic field, with the maximum being set determined on what the supply voltage was. Okay, so that sounds good so far. Now let's have a look at some of the more details. So looking at the table of characteristics here, we can see that that supply voltage can be anywhere between a minimum of 2.7 volts and a max of 6.5. Well, that's perfect. Most Arduinos run at 5 volts, but if you're using an Arduino Pro or a Raspberry Pi or something, that will run at 3.3 volts instead, both well within the ranges of the supply voltage there, so that's not a problem. Now, in terms of how sensitive this particular sensor is, if we come and look at this line down here, so at test conditions of 25 degrees C, so kind of standard operating conditions, we can see that the typical sensitivity is 1.4 millivolts per Gauss. So Gauss is a measure of the magnetic strength, and that's going to increase the closer a magnet gets. But at any given Gauss, the reading that we're going to get, the voltage on that signal pin, is going to increase by 1.4 millivolts for each Gauss of magnetic field detected. So just taken on its own, that value doesn't mean very much yet, but we'll look at that when we consider some of the other sensors that we might want to compare to. Now here's another sensor. This is an Allegro A3144, and Allegro make a lot of Hall sensors, and their numbering system always begins with an A and then 4 numbers, although the actual system used can be a little bit complicated to understand the meaning of those numbers. So as you can see, this one's a bit more expensive though. To get 10 of these, it's going to be £11. They're around £1 each. Now if we look at the datasheet for this sensor, however, we'll see it's laid out in a slightly different way, but we have some similarities. We're again talking about a linear output, so the same as we were with the Honeywell SS49E. But what we can see here is that we have some slightly different sensitivities. So this is actually the data sheet for 3 different models here, but the one I'm using is the A1324, and that has a sensitivity of 5 millivolts per Gauss. So whereas the Honeywell only increased by 1.4 millivolts for each increasing Gauss. This is 5, so it is nearly 4 times more sensitive, and that's going to make it easier to, when you do an analog read on an Arduino or read the input pin on a Raspberry Pi that this is connected to, you're going to notice a larger change in the value from reading that pin than you would do on the less sensitive sensor. Now, this is another chip manufactured by Allegro Microsystems. So this is the A3144, and it's a little bit harder to get hold of than the last chip, so I couldn't find any on eBay. I've had to look on DigiKey, and it's also significantly more expensive again. So to buy one of these Hall sensors costs $2.87. So if we look at the datasheet for it to see if it what the difference is to explain that cost, well, again, we can see it's a linear sensor. It's got an analog output, and it has 5 volt supply. So those are all the same as the other sensors we've looked at. When we then go down to see the sensitivity, however, we can see that this model, which is the one I'm using in this demonstration, the A3144, that's a SIP through hole, now has a sensitivity of 9 millivolts per Gauss. So that is almost twice as sensitive as the A1324, and sort of 7 times as sensitive as the SS49 we looked at, but otherwise has, broadly speaking, exactly the same characteristics. But you do need to exercise some caution because not all Hall sensors behave in the same way. Here we have another Allegro Hall sensor. So this is the A3144. Again, you can buy 10 of them for 99p, and on the face of it, they look very, very similar to the other ones we've looked at. But when you look at the datasheet for this one, there's a couple of important differences to look out for. So when we look through the description here, we'll see that it states that they are unipolar switching devices. And they also get described as an open collector output. So when used with a suitable output pull-up, they can be used as bipolar or CMOS logic circuits. So this Hall sensor works in a rather different way. Rather than having that linear analog output that we were seeing described in the other ones, this one, when not in the presence of an output, it is an open collector. So it's rather like a button that hasn't been pressed. It doesn't read a high signal or a low signal. It has like a floating pin. It has an indeterminate value. So that's why you need to connect a pull-up resistor so that you get a fixed value when not in the presence of a magnet. You pull it up to 5 volts. So where it says this sensor has a unipolar characteristic, that means it only responds to a positive magnetic field, which is what you get from the south pole of a magnet. So when the south pole of a magnet is brought close enough, the Hall sensor will be activated and the output line will be connected to ground. So it will change from an indeterminate state to a low signal all in one go. It's a digital component rather than having any kind of smooth analog response. So this is a rather different type of device, this one. Okay, so we've looked at the theory that magnets have different strengths and sensors have different sensitivities and other properties. Now let's look at a demonstration of what that actually means in practice. So on the board here, I've laid out some of those different sensors that we just looked at the data sheets for, and a read switch at the end. These are wired to input pins of an Arduino here. And then what I've also done is I've laid out some different styles of magnets here on different boards. And I'm going to gradually bring the magnets closer to the readers here. And as I do so, what we're going to do is look at the serial output from the Arduino that's going to show the readings that it obtains from each of those sensors. And this is how those sensors are wired into the Arduino. So if we start off by looking at the right-hand side here with the A1344, and we're looking at the flat side of the sensor. So Hall sensors generally come with a beveled side, and that's where the writing is normally, the logo of the manufacturer. And then they have a flat side, which is normally plain, and that's the side I'm looking at here. So if you're looking at that side, the left-hand leg here is connected to an analog input pin. We're using A5 here. The middle leg is going to ground, and the right-hand leg is going to the 5-volt out from the Arduino. And then when we look at the A1324 next to it, we can see that that is wired exactly the same way. So we've got the left-hand leg again going to an analog input. This time we're using A4. The middle leg goes to ground, and the right-hand leg goes to 5-volt. And these are connected to the ground lines and the 5-volt lines of the other sensors as well. If we jump over one and go to the SS49E, we can see that that too is wired exactly the same way. So we have analog input, this time it's A2, ground, and 5-volt. Okay, now looking at the remaining two devices though, we've got the A3144 and the read switch, and these are slightly more complicated. So remember that the A3144 was described as an open collector device, and the read switch is rather like a button which has got two contacts which are normally open and therefore form an open circuit. So for these devices, the sensor line here, the reading we would get when a magnet is not present is not a determined value. We wouldn't get a high value or a low value. It would just be floating around, and it would be influenced by sort of background magnetism in the environment. So what we're going to do is we're going to pull that to a known value. Now, what you might have used in the past, if you're familiar with Arduino coding, is a pull-up resistor, which is actually in the board itself. And when you activate one of the pins using the pull-up method, that will read a high value by default unless it's grounded. What I'm going to do is something slightly different. So I'm using an external pull-up resistor. So I've got a pull-up resistor here that is connected from the sensor line to the 5-volt line. And I've also got a resistor going to ground though. So what this is going to do, in the absence of a magnet, and it's the same for both of these devices, the sensor line here is going to read halfway between 5-volt and ground. These two resistors here are of equal value. So we've created a voltage divider, and the sensor is halfway in the middle of these two resistors. So voltage across a circuit drops in proportion to the resistance encounters. So if we've got two resistors of equal value in series, and we take a sensor reading in the middle of them, we'll get half of the value of the voltage. So in this case, this device here is going to read 2.5 volts until a magnet is present. Same with the read switch here, it's going to read 2.5 volts, and then when the magnet comes close, the switch will close and it will become grounded and read 0. The reason I've done that rather than simply use a pull-up resistor is because the other three devices here all have what they call a quiescent output of 2.5 volts. So they will read by default halfway in the range between the ground and the voltage supply in these pins here. So I'm making these two devices behave in the same way as the other three, because then that's going to be easier to make a comparison between them. And here's the code that's running on the Arduino. So it's pretty straightforward. It all fits on this one page. There's very little to it. So to start with, we define an array of input pins. This is what the sensors are going to be plugged into. Notice I'm using analog inputs for every sensor, even though I'd say that you'd only get digital input from some of them. I'm using analog inputs. And I've got a total of 5 sensors. There's 5 elements in the array there. In the setup function, we're beginning the serial connection. We'll use that for sending the output to the monitor. And then in the loop function, what we do is we loop over each of the sensor pins in the array. We take a reading from that analog pin of the appropriate sensor pin up there, and we assign that to a variable called val, which we then print to the screen, and we put a comma after each value. Then once we've read every sensor, we use print line just to put an empty line at the end, and that's it. So you're probably familiar with the serial monitor in Arduino. So if we load that up, and we'll see what we get. We'll get tabulated values with 5 readings on each value, which represents the neutral state of the sensor. And you see they're all about 500. So the analog read on an Arduino gives you a value between 0 and 1023. So we'd expect this to be around the midpoint, 512. But there's actually a more useful way of representing that information, which is a serial plotter. And what's this going to do is this will give us a graph of those same values. So you can see we've got 5 lines between 0 and 600 at the moment. That scale will recalibrate in a minute when we get to the end of the page here, if we just wait for a second. Here we go. So we can see we've got 5 different coloured lines between 500 and 540. And there's a key at the top right here. So these are the 5 colours, and they correspond to the 5 sensors in order. So I'll just put a little key at the top of the screen to remind you which one's which as well. So we've got a little bit of noise, but not too bad, and there's some slight variation. And there is my image of my table with my readings on. So if I now place the first set of magnets, I'm going to use the N50 magnets. These are 10 by 3mm circular magnets. I'm going to start off with them being 10 centimeters away. And we don't notice any change in value yet, so I'll slide it a bit closer to 9. Still not much. They're going on there. We'll go through to 8, 7. We'll go forward to 6, and we're seeing a slight rise in the pink value here. So this is the most sensitive reader. This is the A1389. You see it's definitely jumping up there as I get closer, and we also have the yellow one, the A1324, as I get closer and closer. So this is exactly what we'd expect to see. The more sensitive readers, the A1389 and the A132, we're noticing a higher gradient, a sharper gradient there in the increase. Still nothing there. Oh, now they're all noticeably. So I'm only 2 centimeters away now, and you can see a noticeable rise in all of them. But the read switch, oh, okay, so now we have the read switch and the A3144 have dropped to 0. So remember, they ground. If I pull it back slightly, they jump back again. We've got the read switch come back, then the A3144, and we can see the other values return back to their quiescent state, which was about 512. And when I get to about sort of 5 centimeters away, you see no more difference from there on down to the end. Okay, so now let's try that same experiment again, but with some different magnets. Here I've got some N52 magnets, and these are bar style, so they're 10 by 20 by 4, these ones. Again, if I start 10 centimeters away, nothing yet, move it a bit closer, still nothing, 9, 8, 7 centimeters away. Right, now, notice what's happening here, because this is another difference about these magnets, is that these have a reverse polarity. So the other ones I had a north pole facing the sensors. Now I've got a south pole facing the sensors. So see what's happening here to the readings from the A1389, the A1324, and the SS49. They're going down from their quiescent point rather than up, and down significantly there. So we're getting a big change in reading there. There, we've just seen the read switch there has just activated, so very close by, the read switch has dropped to 0. But notice that the A3144 has not changed at all. The green line there is still reading exactly the same as it was. As I move the magnets away, we can see that the others all return to their state. But as I move closer and closer, we'll see them drop. The read switch drops, but the green line does not change the same. So remember that this was because on the datasheet, the A3144 was described as a unipolar Hall sensor. And so with the magnets turned the other way around in this case, it has no effect at all. It's just not changing the response. And if I pass my hand across the magnets, it makes no difference there. So what did that demonstration show? Well, a couple of different things. What we learned from the datasheet is that some sensors give an analog response, smoothly varying in response to the strength of a magnet, whereas some give a digital response, which is that they have a single value until a certain trigger point, and beyond that they change suddenly to another value and just have 2 states. Of those that give an analog smooth response, we also learned that some are more sensitive than others. And we also learned that some sensors are sensitive to the polarity of a magnet. So the reed switch, for example, didn't care which way the magnet was around. That gave a digital signal either way. The A3144 only responded to the south pole of a magnet and didn't respond at all to the north pole. And the other three sensors we looked at rose in voltage in response to one polarity of the magnet and fell in voltage in response to the other. So polarity matters. And it also showed us two other things that perhaps weren't obvious from the datasheet. The first one is that the quiescent value, that is the sort of the resting neutral value when a magnet wasn't there, differed slightly between the different sensors. It was around 512, which was the midpoint of an analog reading, but it wasn't exact. And the other thing was that the readings themselves were quite jittery. There was a bit of noise in that signal. So what we're going to do now is take all that learning and apply it to make a robust escape room prop solution that can use a magnet input. So starting with the choice of sensor. Having looked at the graph from that previous demonstration, it will probably not surprise you to know that I prefer using Hall sensors over reed switches. The reed switch was one of the last sensors to detect the presence of the magnet, and even though it is possible to get more sensitive reed switches than what I was using, they will still only ever have those two states, and they won't be able to differentiate between the poles of a magnet either. Now, the only situation in which reed switches are quite useful is the fact that they are purely mechanical switches, so they don't require any power whatsoever. So if you were creating a battery-powered prop, let's say, and you wanted to reduce the current required by your circuit to an absolute minimal, reed switches can actually be quite useful for that. The other disadvantage of them being mechanical, however, is that they are a little bit more likely to be prone to failure because they actually have moving parts in them, which Hall sensors don't have. So having decided I'm using a Hall sensor, I also ruled out the A3144. It seemed to have all of the disadvantages of the reed switch and no real advantages on top of it. So I'm left with the choice of the SS49, the A1329 or the A1324. For this I'm going to go somewhere in the middle. They basically all had very similar properties except for their sensitivity. Now if I wanted to go very high end I could go A1329, but I think the A1324 will be perfectly good for most of my purposes. So having chosen my sensor, what I then wanted to do was place it as close to the surface of my prop as I could. So whether you're building your dragon's nest or your library shelf or mounted underneath your chessboard, you want to have the beveled edge of that sensor as close as possible to where the magnet's going to be placed. So to do that, I 3D printed this small mount. So you can see on this side there's a small recess for the sensor to go in, and on this side there's a gap at the top here. This is for a set of 3-pin female headers to go there. So if you've ever plugged in a servo motor or something like that, it's the same sort of connectors there. That's going to make it easy for me to connect some cables to the Arduino. On this side there's another recess. That's for a small capacitor to be placed between ground and the 5-volt lines. That's not absolutely required, but it's quite a good idea to have a small capacitor. I'm using 0.1 microfarads here, just to smooth out any jitters. That's going to help with the cleanliness of the reading of the signal. It's not required, but it's a good idea with any components like this. And obviously I've got some holes, some lugs on the side to enable you to screw that in. And here is one that I connected earlier as well. So you can see this one has the Hall sensor mounted in that side, bevel side out, and that will go flush against the inside wall of the component. And on this side I have my capacitor soldered to the ground and 5-volt lines, and I have my sensor line there, and then I can easily plug a connector like this into it. And that's about it for the hardware side of things. So now let me talk through the Arduino sketch I've got running, and particularly point out some of the changes I made from the sketch that was running earlier that was merely intended to show the raw outputs from a range of different sensors. What I've now got is a sketch that's intended as a puzzle controller based on an input from just a single sensor. So the signal out of my A1324, which is the sensor I'm using, is plugged into the analog 0 input on my Arduino. So I define that as sensor pin in the setup here. And as you remember from that graph, in the absence of any magnets, the reading which we'd expect to get on that pin is approximately 512. So the analog input on a Arduino Uno or Nano reads between 0 and 5 and converts that to a digital signal between 0 and 1023. So the default value is normally 512, which is halfway between 0 and 1023. But we did see that it varies slightly as well. So rather than assume that it's definitely going to be 512, we'll create a variable that we initialize at that value. But we're actually going to set that based on an average of some samples, which we'll take in the setup function. This variable here, the sensitivity, so this is how much the reading is going to have to vary above or below this base reading here in order to be determined to be a definite reading of a magnet, so either the south or the north pole of a magnet. If we increase this value here, it becomes less sensitive because the reading is going to have to deviate by more than this amount to be recorded as a trigger. And we'll define 3 different states for this puzzle. So I've only got a single sensor, and that sensor can either read the presence of a negative magnetic field, the presence of a positive magnetic field, or be indeterminately somewhere in the middle. So we'll define those 3 states, and we'll assume that the puzzle starts without a magnet present, so we'll initialize the state in the default setting. Now, the next change I've made, remember I wanted to get rid of some of that glitteriness that we saw in the sample readings. So rather than taking the raw value directly from the sensor and comparing that to the base reading, what I'm going to do is keep a running average of 10 samples. And if the average value exceeds the base reading plus the sensitivity, that's what we'll determine to use the trigger. So you can increase or decrease the number of samples. I'm using 10, which will give you a pretty smooth reading. The problem is if you increase this value too much, that you'll actually get quite a sluggish response because the samples will have to accumulate to a sufficient amount before that average increases. It'll be a much more gradual increase. So you want that value to be high enough to get some smoothing, to get rid of any noise and spikes on the line, but not so high that the code becomes sluggish to respond to input. So I've chosen 10 there, but you might want to fiddle that around a bit. We'll create an array with that number of samples in it, and it's an integer array because the integer values are going to be the values we read from the sensor. We'll also have a total value, so we'll add up the number of samples and we'll add them to a total, then we'll divide by the number of samples to get a mean average. And then this is just a little counter, so we're going to keep 10 samples in this readings array here, and when we've got our 10th sample, what we're going to do is go back to the beginning of that array again and start overwriting the oldest value we had recorded. So this is sometimes called a ring buffer or a circular buffer. We'll keep a running total of the most recent 10 values, or however many values you set in the number sample setting here. And when the average of those most recent sensor readings is compared to the base reading up here, that's what we're going to use to trigger the prop or not. Okay, so we've got a function here. This function we're going to use, so again, rather than taking the raw analog reading, what we're going to do is we'll take an analog reading and we'll add it to our array of samples. So that's what this function does here. So we pass it in the latest sensor reading. We'll increase the total of all the samples by the new sensor reading, and we'll also take off the oldest reading. So that function there, that just keeps the total of all samples in the array up to date. And we'll add the newest sample onto the array itself. This is this counter I was talking about, so we'll move on to the next value in the array. If we get to the end of the array, so if the counter is greater than or equal to the number of samples, we'll simply set the counter back to 0 again. So this will count up the number of elements in the samples array until we get to the total, and then we'll start back at the beginning. We'll just keep on repeating that over and over, just keeping the 10 most recent samples, or however many you define. And at the end of this function, so as well as adding a sample into the array, we'll actually return what the latest calculated average is as well, and we'll return that to the calling function there. So getAverage, which is the function that is called there, that's what's done here. And this is a simple mean average. So we'll take the sample total, that's what was calculated up here, and we'll divide it by the number of samples. So that's a nice simple mean average. Okay, so those are our sort of helper functions. That's what we're doing. So there's not much in there. This is just maths really. We're keeping track of an array of values. We're keeping the total and we're dividing by the number of samples to get a mean average. We're doing that rather than taking just the raw single sensor reading at any one point, just to try to get rid of any spikes that might occur on the line. So in the setup function, we'll begin a serial connection because we're going to be using the output to monitor the values that are received. And to start with, we'll fill up that sample array. So this is what's going to give us that base reading, our background level that the sensor returns when there's no magnet there. So we'll count up the number of samples that we want to take. We'll take a read of the sensor pin and we'll add those number of samples into the array. So we'll loop over and over. So we've now got a filled array full of sample values. And having done that, we'll take the average of all the values that's now in the array and we'll assign that to base reading. And this is what we're going to use from now on for the rest of the prop. If you were to move the prop to a different location, if it's close to a magnetic source or a powerful electric power or something like that, which could affect the level of magnetism, you'd perhaps need to recalibrate that and run the base reading again. But the way this is set up at the moment, it's going to happen every time the prop is started up anyway. So that's fine. And we'll just dump the output to the serial connection so we know what the base reading value was. Then we go on to the main program loop. So on every time through the loop, what we do is we read the sensor pin. But again, as before, rather than doing anything directly with the value of that, what we'll do is we'll add that reading onto our sample array, and then we will return the average from the sample row. So remember the add sample function, which we defined up here. Not only does it add a new sample into the array, but it also returns what the newly calculated average is. So having added our sample on, we'll get the new average, and then we'll use that in all the comparisons from now on. This val here is the new mean average of all the readings. So if the average is greater than the base reading plus the sensitivity, so that means that we are in the presence of a negative magnetic field, because negative causes the signal to rise. So if we weren't already in a negative state, then we'll call the trigger function to say that the signal has risen higher than the base reading plus sensitivity, so we'll call the high trigger, and we'll update the state. So the reason why this bit here is in this extra if state is not state, so this means that this trigger function will only get called once the first time we enter the negative state. It won't get called again unless the magnet is removed and replaced close to the sensor again. We don't want to call this every frame while the magnet is held there. This section here, so this does the same as the section above, but the other way round. So now we'll say, okay, well, if the average value of the sensor readings is less than the base reading minus the sensitivity, so it's fallen below an equal value below as this one was above, this means that we must be in the presence of a positive magnetic field. So again, if we weren't previously in a positive magnetic field, we'll call the low trigger for the first time, because the value is lower than base reading minus sensitivity, and we'll update the state to show that as well. If neither of these are true, well, that means that the value must be within the sensitivity tolerance of the base reading, so it must be less than sensitivity distance away from base reading. So in that case, we'll just set the state to default. We are not detecting a strong enough signal from either a positive or a negative magnet. And then I've just put a short delay in here. This is not absolutely necessary, but there's no reason in a puzzle like this, where we're not doing any absolutely time-dependent data, to run every single frame. So I've just put a short 10 millisecond delay in between each. It'll slow the code down slightly, or to use slightly less power. That's the only reason for that. And then finally, we've got our two functions at the bottom. So these are the functions that are called here and here, and this is where you actually want to place the logic of what's going to happen in your game when this magnet is detected. So we've got a function here, and all I'm doing at the moment is printing something to the serial output. So I'm printing when the low trigger is activated, and I'm printing when the high trigger is activated. But it is in this section here, this is where you actually want to add your game specific logic. So if you wanted to trigger a relay, for example, you could do a digital write to the pin that the relay was connected to and set it low or high, depending on whether you wanted to turn it on or off. Or if you had a 7-segment LED display, you could update that here, or send a message to an MQTT broker, anything you wanted really. This is the part here where you actually add the game specific logic. And that's it. Okay, so finally it's time to demonstrate all that we've learned and put it into action. So here I have my A3144 Hall sensor in my little mount there with the capacitor wired into my Arduino. And here I have an N52 magnet, so this is the same sort that I was using in the demonstration earlier. So if I just fire up my Arduino serial monitor window so you can see what's happening here. I've just started the sketch, and you can see that it's initialized with a base reading of 517. Now, as I bring the magnet closer, what I hope is we'll get to about here, and you'll see that the high trigger has been activated at that distance. I hope you can see that. That's about 4 centimeters, I would say. If I remove the magnet, we get no trigger, and place it back in again. Each time I bring it close, that way up, I get a new high trigger being detected. Now if I turn the magnet round, I get the other side facing the sensor instead. At the same distance, I get the low trigger activated. So I think that's a pretty useful, pretty robust solution for many escape room puzzles. We've got a sensor which will be triggered and can trigger a relay or a maglock or whatever you want it to do when any item that has a magnet embedded in it is brought to about that distance. But not only that, we can actually use this for object identification as well as detection. So in its most trivial sense, you could have two different objects, one with a magnet screwed that way around and one with it screwed that way around, and have them trigger different things on the Arduino. But you could also have an array of sensors on the board here, and depending on the pattern of the polarity of magnets placed, if you had an item that had several different magnets at different spacings, that could actually be used to detect different objects as an alternative to RFID, which is the technology commonly used for that kind of puzzle. So that's pretty much all I can say about magnets and magnetic sensors. We've looked at hardware and software and tuning settings and lots of different things. I hope you found that useful and informative, and if you do use any of this in an escape room puzzle you're creating, please let me know. I love to see what people do with them. If you'd like to access the Arduino code download or the links to where I bought these various components and things from, or the 3D model for my little Hall sensor out there, please do check out my Patreon page there where I have links to all the projects I've done. And if you would like to, and if you feel able to support me there, that would be amazing as well. But if you can't, I will continue putting these videos up on Facebook. Anyway, do let me know if you have any questions or comments below, and I look forward to seeing you next time. So thanks very much for watching.